screws, fasteners, and the design of non-permanent joints. Lecture slides. Chapter 8. Screws, fasteners, and the design of non-permanent joints. Copyright 2015 by McGraw-Hill Education. This is proprietary material solely for authorized instructor use, not authorized for sale or distribution in any manner. This document may not be copied, scanned, duplicated, forwarded, distributed, or posted on a website, in whole or part. Chapter outline. Shigley's mechanical engineering design. Reasons for non-permanent fasteners. Field assembly. Disassembly. Maintenance. Adjustment. Shigley's mechanical engineering design. Thread standards and definitions. Pitch, distance between adjacent threads. Reciprocal of threads per inch. Major diameter, largest diameter of thread. Minor diameter, smallest diameter of thread. Pitch diameter, theoretical diameter between major and minor diameters, where tooth and gap are same width. Figure 8.1. Shigley's mechanical engineering design. American National, Unified, Thread UN Normal Thread. Standardization. The American National, Unified, Thread Standard defines basic thread geometry for uniformity and interchangeability. American National, Unified, Thread. UN Normal Thread. UNR greater root radius for fatigue applications. Metric thread. M series, normal thread. MJ series, greater root radius. Shigley's mechanical engineering design. Not good for vibrations. The normal thread to specify fine series UNF. Standardization. Coarse series UNC. General assembly. Frequent disassembly. Not good for vibrations. The normal thread to specify fine series UNF. Good for vibrations. Good for adjustments. Automotive and aircraft. Extra fine series UNIV. Good for shock and large vibrations. High-grade alloy. Instrumentation. Aircraft. Shigley's mechanical engineering design. Basic profile for metric M and MJ threads shown in Figure 8.2. Standardization. Basic profile for metric M and MJ threads shown in Figure 8.2. Tables 8:1 and 8:2 define basic dimensions for standard threads. Figure 8.2. Shigley's mechanical engineering design. Diameters and areas for metric threads. Shigley's mechanical engineering design. Diameters and areas for unified screw threads. Table 8:2. Tensile stress area. The tensile stress area, AT, is the area of an unthreaded rod with the same tensile strength as a threaded rod. It is the effective area of a threaded rod to be used for stress calculations. The diameter of this unthreaded rod is the average of the pitch diameter and the minor diameter of the threaded rod. Shigley's mechanical engineering design. Square and Acme threads. Square and Acme threads are used when the threads are intended to transmit power. Figure 8.3. Table 8:3 preferred pitches for Acme threads. Shigley's mechanical engineering design. Mechanics of power screws. Used to change angular motion into linear motion. Usually transmits power. Examples include vices, presses, jacks, lead screw on lathe. Figure 8.4. Shigley's mechanical engineering design. Mechanics of power screws. Find expression for torque required to raise or lower a load. Unroll one turn of a thread. Treat thread as inclined plane. Do force analysis. Figure 8.5. Figure 8.6. Shigley's mechanical engineering design. Mechanics of power screws. For raising the load. For lowering the load. Figure 8.6. Shigley's mechanical engineering design. Mechanics of power screws. Eliminate n and solve for p to raise and lower the load. Divide numerator and denominator by cos and use relation tan equals L/PDM. Shigley's mechanical engineering design. Raising and lowering torque. Noting that the torque is the product of the force and the mean radius. Shigley's mechanical engineering design. Self-locking condition. If the lowering torque is negative, the load will lower itself by causing the screw to spin without any external effort. If the lowering torque is positive, the screw is self-locking. Self-locking condition is PFDM greater than L. Noting that L/PDM equals tan L, the self-locking condition can be seen to only involve the coefficient of friction and the lead angle. Shigley's mechanical engineering design. Power screw efficiency. The torque needed to raise the load with no friction losses can be found from EQ 8:1, with F equals 0. The efficiency of the power screw is therefore. Shigley's mechanical engineering design. Power screws with Acme threads. If Acme threads are used instead of square threads, the thread angle creates a wedging action. The friction components are increased. The torque necessary to raise a load, or tighten a screw, is found by dividing the friction terms in EQ 8:1 by cos. Figure 8.7. Shigley's mechanical engineering design. Assuming the load is concentrated at the mean collar diameter DC. Collar friction. An additional component of torque is often needed to account for the friction between a collar and the load. Assuming the load is concentrated at the mean collar diameter DC. Figure 8.7. Shigley's mechanical engineering design. Stresses in body of power screws. Maximum nominal shear stress and torsion of the screw body. Axial stress in screw body. Shigley's mechanical engineering design. Stresses in threads of power screws. Bearing stress in threads. Where Nt is number of engaged threads. Figure 8.8. Shigley's mechanical engineering design. Stresses in threads of power screws. Bending stress at root of thread. Figure 8.8. Shigley's mechanical engineering design. Stresses in threads of power screws. Transverse shear stress at center of root of thread. Figure 8.8. Shigley's mechanical engineering design. Stresses in threads of power screws. Consider stress element at the top of the root plane. Obtain von Mises stress from EQ 5 to 14. Shigley's mechanical engineering design.